Today we're going to continue our conversation related to slope. However, we're going to talk about something called direct variation. And what it is, it's basically an equation described by the formula or the equation y equals kx, where we know k is not equal to 0. And we call k a constant of variation. So in this case, we look, here's y equals kx. The number right before the x is the constant, so k in this case is equal to 2/3. And we see that there's a line right here describing that. Another way to talk about direct variation means as x increases, then y increases, or as x increases, as x decreases, y decreases. And we can see that in our next slide. In this case, here's my y equals kx form, and k in this case is -1/4. And you can see x is decreasing here, and so is y. So as one goes up, the other goes up. As one goes down, the other goes down. Now, one of the things you're also going to notice is that the variation constant in each of the lines that we've talked about is actually the slope. And each graph in a direct variation is going to go through 0, 0. Let's just go back and take a look at our first two slides again. And let's look at the variation constant of 2/3 here. If we take a look at the slope of this line, here's another point on that line, and if I go up 2 and over 3, we have a rise over a run equaling 2/3, which is our slope, or the change in y over the change in x. We look at the second slide, and we find another point that line goes through. It appears that here's one right here, and if I were to go down 1 and over 4, there again is our slope. So let's go back to this problem over here, and we want to take and graph this direct variation of y equals 2/5 x. Well, we just found out that in a direct variation, all direct variations go through the point 0, 0, and our variation constant is going to be our slope. So our slope m is equal to 2/5, which is equal to our rise over our run. So we go up to 2, over to 5, put a dot there, and then draw a line connecting the 2 points. Now if we want to be accurate equally on the other side, we go down 2 and back 5, putting another dot, connect those dots. And there's our direct variation. Sometimes direct variations can be written in this form, and there's a couple of ways to solve these. It says suppose y varies directly as x, and y equals 9 when x is equal to 3. Well, we said before, direct variation is y equals kx. So you'll notice it says y varies directly as x. The first term is always isolated by itself, and if it varies directly, then the thing that it varies directly as is on the other side of the equal sign with the k. So in this case, they give us a value of 9 for y and 3 or -3 for x. So I could actually fill that into this equation. Notice I'm missing k. What this will enable me to do is actually find k. So if I were to solve this, I'd divide both sides by -3, and I would get k equals -3. Thus, my direct variation equation is y equals -3x. But then notice there's a second part. It asks me to write direct variation equation, which I just did, but then I want to use that equation to find the value of x when y is negative 36. So they've given me a second case in this problem. They've told me, hey, what is x if my y value is now negative 36? Well, the only difference between this part of the problem and the initial is I didn't have k before, and now I do have k. So I have negative 36 is equal to negative 3, because that's my k value once again, times x. And then I can simply divide by negative 3 to both sides. Oops, sorry. And I end up with positive 12 is equal to my x value. Now, another word for direct variation is also directly proportional. And sometimes what I like doing when I do a direct variation is looking at the problem in this way. Notice in this problem I had two cases. I had some y1, or first case, times my variation constant, that's always the same, was equal to whatever that first case was in terms of x. And then I had a second case given to me where I had some second y equaling the same k times the second x. Now notice in each case I can divide each side by my x term. Here I get y1 over x1 is equal to k. And notice divide by x2 in each case. And I get y2 over x2 equals k. And in this case, you'll notice that this term is equal to k, and this term is equal to k. If both those terms are equal to k, then they're also equal to each other. And this is why I say a direct variation is also the same as directly proportional. So here's my proportion. Now, the problem said that I have two cases. Y equals 9 when x equals negative 3. That's case 1. And x is unknown when y is negative 36. That's case 2. So notice my proportion set up in case 1 and case 2. My first y was 9. My first x was negative 3. My second y was negative 36. And my second x was unknown. So now notice I've got a proportion sitting right here, which I could solve using a cross product. I could say 9 times the second x is equal to positive 108. Now I can solve this for x by dividing both sides by 9. And the second x is equal to whatever 108 divided by 9 is. Last time I checked, about 12. So if you look, I actually got the same solution as I got the other way. So there's two ways to do this. I'm more inclined to use a proportion for my variations than plug into two different equations. So I'm going to use that technique on the next problem. It says we have the cost of bananas varying directly with the weight. So if I were to write a direct variation equation, the cost varies directly with the weight. So C equals KW. That's kind of in a Y equals KX form, except the Y is the bananas in this case, and the X is like the weight. So now the problem asks me to write the equation that relates the cost of the bananas to their weight. And here is that equation. Then it says find the cost of a quarter pound of bananas. Well, what I could do is I could find the K value, solve, and then plug these problems back in, or I can just set up a proportion. Here's my case 1. And then here's case 2. So in case 1, I know I'm going to have some C1 over W1 is equal to C2 over W2. So the cost is 1.12 over the initial weight of 3.5. And that should be equal to the unknown cost over the second weight. 4¼ pounds is 4.25. So if I take 1.12 times 4.25, which is a cross product, that should be equal to 3.5x. 1.12 times 4.25 is 4.76. That's equal to 3.5x. Divide both sides by 3.5. And in that case, x is equal to 1.36. So, and that's a dollar value. So you've seen a couple of ways we can set up and solve these direct variation problems. One way is in a proportion. The other way, we go back here, is to take and find a K value, write a new direct variation equation, and then plug back in your second case to find the missing value.